All right, let's do some example problems. We're going to do 2 example problems, and for 2.5, I don't know what number I'm on. So we're going to skip numbering and say this is example blue. We'll go colors for these examples. And this has a water trough, and this water trough is 15 feet long. And the ends of the water trough are shaped like upside down triangles. And the base of those upside down triangles is 8 feet. That's going to be like this. And the height is 3 feet. Height of that triangle is going to be like that. Picture not drawn to scale. And we're curious about the force on one end of the trough when it's full. So really, right, what we've got here is we've got a trough that looks like the... hold on. Try it a little better. Right, the trough looks like this. Right. And then, there's water at the top. Kind of like this. And we're curious about the force on one of the ends. So we're curious about the force on this green side of the trough. Again, we just look at that green side and we say, okay, it has a base of 8 feet. It has a height of 3 feet. What's the pressure on this triangle? So we just set this up, or sorry, the force, rather. We set this up just like we did at the last video. We know the force will be with you always. Ha, ha, ha. What a great Star Wars joke. The force is just going to be the weight density of water, because it's full of water, we're assuming. There could be other liquid. We're dealing with water here. Times the integral from a to b of whatever that width function is, times whatever the depth function is with respect to x. And that's it, right? Just using this handy dandy little formula. And all we have to do is find out what's the width and what's the depth. So we need to just identify variables. So let's say that x is, x can either be how far we are from the bottom or how far we are from the top. Your call. Your call what that x is. Let's have x be depth from the top. X is distant. Then we can be consistent with that pumping section. X is the distance from top of the water. Okay, well then that right away tells us that this force, which rho value are we using? We're using imperial units here. So we're going to need that 62.4. What was it? The units were like pounds per feet cubed or something like that. Times the integral. Well, if x is the distance from the top, we're going from 0 up to 3. Right, we're starting at the top. We're all the way going down to a depth of 3. You could also say depth of water rather than distance of the top from the top. Works out either way. And now we need the width function. So at any depth, what's the width? Well, when x is equal to 0, the width function is, well, it's 8. When we're at the very bottom, what's the width? It's 0. And in fact, we know it's linear. If it weren't linear, it'd be a little bit more complicated. But because it's a line, those 2 points are all we need. There's a couple ways that you could set this up. You could call this the origin. You could call this the origin. And you could find the actual equation of the line and use that to find the width. But because we know the width scales linearly with depth, we can just use this to find this width function anyway. Find the equation of this line with these 2 points. Well, the slope of this line is what? It's the y2 minus y1 divided by x2 minus x1. It's negative 8/3. And then we can use point slope form. Y minus any of the y coordinates Let's use this point, because then that's just y minus 0 equals the slope times x minus the x coordinate. And instead of using y's, since we are talking about w here, we could write this as a w as well. And that's our width function. It's negative 8/3 times x minus 3. All that's left is the depth function, and we're done. Easy. Well, x is the distance from the top. So when we are x units from the top, what's our depth? They're literally the same thing here. Our depth is just x. So s of x is just x. S is the depth. But, and we had choices on this, we chose x to be the distance from the top. We didn't have to. X could have been something else, and that would have changed the width function and changed the s function, but you get the same value if it's your integral. Now we evaluate this integral, and then we're done. If you'd like to see me evaluate this integral, stick around till the end of the video, but it's just chapter 1, evaluating an integral. So I'm going to do it at the end of this video, but I highly recommend you pause the video right now and do it on your own. And I'll work through it at the end. We're going to close this video with example red to make a musical reference. I could say The Blood of Angry Men. Any Les Mis fans out there? But we're going to do this from the book. I don't want to write this all down. We're returning to good old Hoover. Hoover Dam. Okay. So as you can see here, this dam is not straight. This curve is not straight. And that's fine. We could calculate this. But the book is saying, we're going to take it easy on you a little bit. And let's assume that it does have straight sides. So this is the face of the dam. These are two pictures and diagrams are oriented the same direction. And again, the dam is thicker on the bottom, right? It's thicker this way, if you see into the picture. But we're just looking at the face of the dam that's touching water. And it's easier to look at this from this direction rather than the other direction, which would be underwater. And we're curious about, okay, how much all this water, what's the actual force of all this water on the dam with these dimensions? And it says, okay, when the reservoir is full, Lake Mead's maximum depth is 530 feet. So even though the dam is 750 feet, the max depth of a full length is only 530 feet. So the water only goes down this low. So the water of the lake does not go all the way down here. Water of the lake just goes down here or something. And the surface of the lake is 10 feet below the top. So it's really only going from about here to like right here. And there's another beautiful diagram of this. Another trapezoid. Didn't we just do a trapezoid? No, we did a triangle. But as you'll be able to see, trapezoid and a triangle are almost the same, just with different limits. So two questions. Part A, find the force on the dam when the reservoir is full. And again, a full reservoir is when it's 10 feet from the top. You do not want, you don't want it going over the top. All right. I guess I actually don't know too much about the physical situations, but that's what we're looking at here. So first, we're looking for this force. And I'm going to copy down this image because this is the image that we're going to use. And specifically, I'm going to copy down only the portion that has water because that's what we care about, right? There's no the water is not exerting a force on this part. The water is not exerting a force on this part. Now, of course, the water is exerting a force on this part, and this part would in turn maybe have other forces that relate with other things. But the direct hydrostatic force is just this trapezoid right here in the blue. And that's what I'm going to copy down because that's what we're going to be using for our calculations. So the height is 530 feet. What other things do we know? Oh, wait. What other things do we know? We know it's 1250 feet at the top. How much is it 10 down? Okay. We're going to need a second picture. So this white diagram is important to fill in the blue diagram. So the white, this is 750. This is 750. These are in feet. And the top is 1250. So we only care about the white to get the blue. And again, there's a lot of different ways that you can look at this. Actually, I don't even think we need anything more in the blue. Not really. But we can if we want. There's a lot of ways that you can do this. Actually, it might make a little bit more sense. Have white and blue on top of each other like this. A lot of ways that you can do this. So again, this is 10 feet right here. And if this is 530, we also could tell what this distance was, but we don't need it. What's important, and the reason why I'm kind of backtracking a little bit, is what's our end goal? Our end goal is looking at the total force. And we need a width formula. And we need a depth formula. And there's a lot of ways that you can set this up. There's like 5 different integrals that I can think of off the top of my head. And your integral might be different than my integral, but they should give the same number. All right. Let's set this up the same way we set up example blue, the first example of this video, okay? So let x be the distance. So here the distance is not the same as the depth. The distance from the top of the dam. So for example, a distance of x equals 20 would only be a depth of 10. Right? Because there's that 10 feet under the dam. This is not the only way to set this problem up. You could have x be the depth, but then it's a little bit more tricky. You'd really need the dimensions of the blue trapezoid. Whereas if we let x be the distance from the top, we don't actually need the dimensions of the blue trapezoid. Lots of ways to set this up. We can all do it differently. Maybe there's a finite number of setups. Nope, there's an infinite number of setups. I could prove that, but we don't care about that. Let's do the problem. So if x is the distance from the top of the dam, now we're going to need the width at any x. Again, we're going to need this width function at any x like this. And then we're also going to need the depth function too, right? And that'll be the depth. So I think the depth is a little bit more straightforward here, right? The depth is just going to be x. It's going to be really close to x, right? The depth is just going to be 10 foot shorter than x. Right? It's whatever x is minus 10. Because if this distance right here is 10, the depth is 0. If this distance is 20, the depth is 10. This distance is 50, the depth is 40. So just getting that correlation between the depth and the distance from the top of the dam. All right. And what is x? Let's just start filling things in, right? Wow, my row is really getting out of control. We're integrating from a to b. What are our limits for x? Where x is the distance from the top of the dam. So we're starting at the top of the water. That's an x value of 10. On s value of 0, an x value of 10, we care about x because this is an integral with respect to x. And it's going all the way to the bottom of the water. The water is 530 feet deep. The x value will be 540 feet from the top of the dam. We know the depth is just x minus 10. Again, we could do it. Another integral we could do would be to do a u substitution, right? If this is our u, then u would be the depth of the water. And we'd go from 0 to 530. But we don't need to. You can have x, you can have x be whatever you want. All we need is the width. All we need is this guy. And we set up this width function the same exact way we did it in example blue. We say, okay, we know when x is equal to 0, that the width, well, there's no water when x is equal to 0, but if there were, the width would be 1250. And we know that when x is equal to the bottom, 750, again, there's no water there, but if there were water, we know the width would be, 750. Right? At the bottom of this trapezoid, the width is 750. And we didn't have to solve for these at all. They were given to us. But if we only used the blue trapezoid, we would have had to solve. So again, this is a linear relationship. Now, if it were the actual Hoover Dam, right, this is not actually a line, the width function would be more complicated. Everything else would be the same so far. It'd just be the width function that's more complicated if the shape changes. So what's the slope? We use the slope to find the formula of that width function. It's going to be a line. It's a line because we have a trapezoid. So change in y, second y minus first y, over change in x, second x minus first x. This is our slope. It's going to be negative 500, I believe, on the top. Over 750, that's negative 2/3. Okay. Negative 2/3, great, that's our slope. So then the width function minus the y value, choose any one you want, equals the slope times x minus that x value. Whatever y value you choose, we have to use the same x value. In other words, the width function is negative 2/3 x. Oh no, I'm writing behind my head again. Negative 2/3 x plus 1250. And when you do this line stuff, what you should do is, again, just check that this line that we have fits with the two data points that we have as well. All right. I'll go see through so you can still see things. So again, at a distance of 0 from the top, good, we have 1250. That's what we wanted. At a distance of 750 from the top, negative 2/3 of that's negative 500. 750 is the width. Good, that's what we wanted. So this is an equation that satisfies both of those points. So there we go. That's our width. Negative 2/3 x plus 1250. And fun little fact, if we actually did let x, or if we did that u substitution, or if we let x be the depth of the water, then this step becomes a little easier, but it's fine. This is perfectly reasonable. And again, we're dealing with feet, so we're going to use that value of 62.4. 9,800 if, it is pounds per feet cubed. I think that's what I guessed. Or maybe I got it backwards, the reciprocal. Now we just evaluate this integral and we're done. Again, that's the end of the video. That's all the new stuff. If you want to stick around, I highly recommend you calculate each of these values, make sure your answer is expressed in the right units, and then see if we got the same thing. But that's it. So feel free to say bye-bye. Okay, but the rest of this video, I will actually calculate these out and check our answers. Then this first one, we can factor out an 8/3. It is divisible by 3, but I'm just going to multiply 62.4 by 8/3 with a calculator. We got 166.4 with a negative. And then integral from 0 to 3 of this red guy. To do this integral, we need to distribute. So we distribute x squared minus 3x. With respect to x, now we take that antiderivative. Now we're going to get 1/3 x cubed minus 3/2 x squared from 0 to 3. Now we can evaluate. When it's 3, we're going to get 1/3 times 27. 3 cubed is 27. Minus 3/2 times 9. Minus, when we plug in 0, we just get a big fat 0. So negative 166.4 times this becomes 9 minus 27/2. And 9 is going to be 18. Whoa. Yeah, 18/2. So we should get negative 9/2 times this other thing. If we do that, I just erased the thing I wanted. Negative 166.4. We get 748.8. Ah, my pen's upside down. 748.8. What are the units? We're talking about force. And we're using the imperial system. So it's going to be pounds. This was the water in the trough. 750 pounds is the force of that water on that side, on just one end, on that one end of the trough. And again, 750 pounds on the other end of the trough as well. It's a lot of force. It's a lot of weight. Okay. Interesting. That's more than I would have expected, but I guess it is pretty wide. 8 feet wide, 3 feet deep. It's a lot of water. That's like, how many of me? I can't do that math. Like 4? Roughly 4 of me standing on, if the trough were sideways. Anyway, we can also do it with this guy. Let's evaluate this one on the second half. Also, I was smart before this video. I wrote the answer down, so I know that's the right answer. But we could check it on Desmos as well. So if we do this one, we have the, we're going to have to FOIL this out. 62.4 times the integral from 10 to 540. When we FOIL this out, we got to be very careful, Jason, not to make mistakes. Negative 2/3 x squared plus 1250x minus, plus. All right, FOIL first, outer, inner last. Oh, I did inner first. I did file instead. All right, so we need the plus 10 times 2/3 x. So plus 20/3 x. Gosh, I don't want to do this by hand. Minus 12,500. But I'm going to. Because I'm making you guys do it, so I need to do it too. All right, now we can combine like terms. 1250x plus 20/3. 1250x, multiply that by 3. It's 3,750 over 3, right? We can combine like terms to get negative 2/3 x squared plus 3770, that plus 20, thirds x minus 12,500. Now we can use the power rule to evaluate this antiderivative. And we're going to get negative 2/9 x cubed plus 37. We're dividing this by 2. We can do that right now, right? Dividing this numerator by 2. Can I do this now? 18 would give us 3,600. We have 170 left. 170 divided by 2 is 85. Squared minus 12,500x. Yeah, all right. 3,770 divided by 2. I want to make sure. 1885. Great. I wasn't even worried. Now we plug things in and okay, this is where things are going to get squirrely. 62.4. I'm going to plug these in on a calculator. The 540 first. So let's say f of x is equal to what we just wrote down, negative 2/9 x cubed plus 1885 over 3. X squared minus 12,500x That'll be our function, and we're curious about what is this function evaluated at 540? It's 141, 480 minus, what is this when we plug in 10? So when we plug in 10, we get a negative number. So when you subtract that, it becomes a positive. Plus 62, 388. Sorry, that's a comma. And that 8 repeats as a decimal. So when you add those together and multiply by 62.4, we get the correct answer. That's good. This is a big number, right? 8.832. Well, let's say approximately 8.832 times 10 to the 9th. And that's going to be in pounds here. Now, usually we'd convert this to tons. Even if we convert this to tons, it's a huge number. But you could convert it to tons. And it's a good practice to convert it to tons. All right. Neat. We calculated the right answer. Oh, crap. I said that was the end of the video. But there was a part B to this video. All right. How important is part B? Okay. It just changes the problem. Part B, you can do it. You can do it. All right. It just changes the blue trapezoid. Everything else should be the same for part B. It just changes your blue trapezoid, which really just changes your depth function and your region of integration. So good luck. You can do it. I believe in you. Let me know if you have any questions. Bye-bye.